My name is Doug Ramsey. I'm a professor in the Department of Wildland Resources at Utah State University. This video is part one of three short videos that describe the Landsat Analysis Ready Data, or Landsat ARD product developed by the U.S. Geological Survey. These videos are supported by AmericaView, which is a nationwide consortium of university-led, state-based remote sensing scientists funded primarily by a grant from the U.S. Geological Survey. These scientists work to support the use of Landsat and other public domain remotely sensed data through applied research, K-12 higher and higher STEM education, workforce development, and technology transfer. This first of three videos introduces the Landsat ARD product and provides data organization, the rationale, and a bit of history for context so future users can better understand these data. The second video will discuss the data organization and the various image products available through the ARD product. The third video will present an example of how these data can be used to monitor and assess landscapes. The U.S. Geological Survey and NASA have worked hard over the past years, and particularly over the past 2 decades, to make Landsat data more available and accessible to scientists, land managers, and the general public. Detailed information about the Landsat Analysis Ready Data product can be found on the Landsat ARD homepage, located simply by Googling Landsat ARD. On that page, you will find detailed information, including the Landsat ARD Data Format Control Book, which documents how each data product were processed, their data formats, and detailed explanations about quality assurance layers. The Landsat ARD product can be downloaded using earthexplorer.usgs.gov. For those of us familiar with the Landsat program, we know it began with the launch of Landsat 1, originally called the Earth Resources Technology Satellite, in 1972, and this program has been in continuous operation since then. The Landsat ARD product currently includes data from Landsats 4 through 8 and includes imagery from the Thematic Mapper, Enhanced Thematic Mapper, and Operational Land Imager spanning 1982 to the present. The Landsat platforms have a 16-day repeat cycle. When two platforms overlap in time, the opposing orbits provide an 8-day repeat cycle. Typically, when searching for and downloading Landsat imagery, we refer to the Landsat World Reference System, which identifies the geographic location of individual image frames. Landsat imagery is referenced using a path row system, where paths represent individual orbital paths and rows segment each path into individual frames. Therefore, if we are interested in a particular location on the Earth, we would identify which path and row covers that location and download that image frame. For the purpose of this tutorial, I will be using imagery located in the southwestern corner of Utah, which is covered by Path 38, Row 34. If we examine the path row frames, we can see that between paths, there's a significant amount of overlap. This overlap increases as we move north. The Landsat ARD product takes advantage of this overlap so that users can increase their probability of attaining high-quality, cloud-free imagery at a greater frequency than the 16-day or 8-day, when we have two sensors in orbit, repeat cycle. To make it easier for the user to locate and download imagery from the adjacent overlapping path, the USGS has reframed the image path row reference system into a systematic grid covering the conterminous US, as well as individual grid frames covering Alaska and Hawaii. Each cell or tile in the grid covers an area of approximately 150 kilometers squared. This provides an image frame consisting of 5,000 by 5,030 meter pixels. All images that intersect any portion of a specific tile are subset to that tile and stored individually. The grid system, and therefore all imagery, are projected to the standard USGS Albers Equal Area Conic WGS84 projection. The Hawaii grid uses the same projection as the conterminous US. Alaska, however, uses a modified Albers Equal Area Conic projection. This represents a departure from the universal transverse Mercator projection typically used for Landsat imagery in the original path row frames. The image that I identified earlier, falling on Path 38, Row 34, is approximately located in grid H7, V10 of this graphic. Zooming into this grid tile and superimposing the path row reference system, we can see that there are approximately 8 different images that intersect H7V10. Placing the path 38, 34, row 34 image over the H7V10 grid shows us how the image, the original image, can intersect multiple ARD grids. For our H7V10 grid, however, only that portion that falls within is retained. To show how this works for adjacent paths, here we have the path 38 row 34 image with the surrounding path row frame superimposed. Replacing the path row frames with the ARD grids, we can see that portions of the image, of the original image, also occupy adjacent tiles. Clipping the image to the H7V10 tile leaves us with a subset of the original image. This subset is stored as an individual Landsat ARD tile. If we then look at the adjacent path 39 row 34 image located to the west, we can see the overlap with the path 38 row 34 nominal boundary, identified by the red lines. Superimposing the ARD grid system, we see that just the northeastern corner of path 39 row 34 image falls into the H7 V10 tile. Clipping this image by the H7V10 tile, we retain only that portion of the image, and that portion is stored as an individual Landsat ARD image frame. By clipping only the portions of the adjacent images that fall within a specific ARD tile and storing each clip as an individual frame, the process reduces the work users need to do to identify, download, clip, and process overlapping images. In this example of a 32-day period, or 2 full Landsat orbital cycles, we have a total of 13 individual tiles with potentially usable data collected by Landsat 7 and 8. If our study area is located on the western portion of this tile, we have a total of 9 possible dates, and the same amount if the east side is our study area. The central diagonal portion, of course, does not have east-west overlap and is therefore limited to the 5 images collected as a result of the 8-day orbital cycle provided by the 2 sensors. This amount of overlap depends on latitude. As a result, for tile H7V10, there are 3,527 Landsat 4, 5, 7, and 8 images intersecting the grid from 1982 through the end of 2020. In comparison, for the path 38 row 34 image, there are approximately 1,200 collection 1 level 1 images available for the same time period. The goal of the Landsat ARD product, therefore, is to organize and package the data to increase the frequency of revisit as well as to simplify the processing needed by users to achieve the same temporal density of data. To visualize this in a different way, I use a short Python script to overlay all 3,527 temporal slices of H7V10 and count all non-fill or actual data pixels to generate this pixel revisit frequency layer. Blue areas represent pixels that have no overlap with adjacent images. These account for 30 to 35% of the 3,527 images. Red areas represent a maximum temporal frequency of 56 to 60% of the 3,527 images. By reorganizing individual path row oriented images into this grid system, the USGS has generated a data set that provides the user with quick access to standardized images that have a higher temporal frequency than the standard path row organization.